Fluid-structure interaction, or FSI, is a captivating field of engineering that explores the intricate dance between fluids and structures. It delves into how these entities interact and influence each other's behavior. Imagine the wind caressing the wings of an airplane, the water rushing over a dam, or blood flowing through our arteries. These are all examples of FSI in action. In essence, FSI studies how forces exerted by fluids cause structural deformations. Simultaneously, it examines how these deformations in turn alter the flow of the fluid. This interplay between fluids and structures is ubiquitous in the natural world and plays a crucial role in countless engineering applications. The significance of FSI in engineering cannot be overstated. From designing aircraft and spacecraft to developing reliable biomedical devices and optimizing energy systems, FSI analysis is essential. By understanding and predicting how fluids and structures interact, engineers can create more efficient, reliable, and innovative designs. Take, for instance, the design of a wind turbine. The blades of the turbine must withstand tremendous aerodynamic forces generated by the wind. FSI simulations allow engineers to analyze these forces and optimize the blade design for maximum energy capture while ensuring structural integrity. To unlock the secrets of FSI, engineers employ various modeling approaches, each with its own strengths and limitations. These approaches differ in their complexity and computational demands, and choosing the right one depends on the specific problem at hand. One-way FSI. This approach is the simplest, where the fluid flow affects the structure, but the structural deformation does not significantly impact the fluid flow. Imagine a flag fluttering in the wind. The wind's force influences the flag's shape, but the flag's movement doesn't significantly alter the wind's flow. Two-way explicit FSI. A step up in complexity, this method considers the influence of structural deformation on the fluid flow, but it does so in a segregated manner. The fluid and structure are solved separately, exchanging information at each time step. This approach is suitable for problems where the interaction between the fluid and structure is relatively weak. Two-way implicitly coupled FSI. This approach solves the fluid and structure equations simultaneously, accounting for their interdependence more accurately. It's like solving a complex puzzle where each piece influences the others. The solution requires considering all parts together. Fully coupled FSI, the most computationally intensive approach, fully coupled FSI solves the fluid and structure equations as one monolithic system. This method is reserved for the most demanding FSI problems where highly accurate and tightly coupled solutions are paramount. ANSYS Workbench, a powerful engineering simulation software suite, offers a comprehensive platform for tackling FSI challenges. Its intuitive interface and versatile tools empower engineers to simulate and analyze complex FSI phenomena with ease. Within ANSYS Workbench, several workflows cater to different FSI scenarios. Co-simulation. This workflow is ideal for two-way FSI problems where a strong interaction exists between the fluid and structure. It involves using separate solvers for the fluid, typically ANSYS Fluent, and structure, typically ANSYS Mechanical domains, and allowing them to exchange data at specified intervals. Static data transfers. As the name suggests, this workflow involves transferring data between the fluid and structure domains only once. It's suitable for problems where the structural deformation is small and doesn't significantly affect the fluid flow. Fluent mapping panels. This workflow provides a streamlined approach for transferring data between ANSYS Fluent and ANSYS Mechanical within the Workbench environment. It simplifies the data exchange process, making it easier to set up and manage FSI simulations. Let's delve into the steps involved in setting up a co-simulation FSI analysis in ANSYS Workbench. This workflow is particularly well suited for problems with significant fluid structure interaction. First, define the geometry by creating or importing the geometry of the structure and the fluid domain. Next, generate the mesh, a discretization of the geometry into smaller elements which are used to solve the governing equations. A high-quality mesh is crucial for accurate FSI simulations. Then set up the mechanical analysis in ANSYS Mechanical by defining the material properties, boundary conditions, and loads acting on the structure. This setup provides the structural response to the fluid forces. After that, set up the Fluent analysis in ANSYS Fluent by defining the fluid properties, boundary conditions, and initial conditions. This setup characterizes the fluid flow behavior. Finally, establish the system coupling. This crucial step links the mechanical and fluid simulations, allowing them to exchange data and influence each other. Define the interface between the fluid and structure, specifying how data is transferred. Section 5, Geometry and Meshing, the foundation of accurate FSI simulations. Accurate FSI simulations hinge on a robust foundation, geometry and meshing. These two aspects are intricately linked and play a pivotal role in determining the accuracy and stability of the analysis. The geometry defines the physical boundaries of the problem, while the mesh discretizes this geometry into smaller elements, forming the computational grid on which the governing equations are solved. The quality of both the geometry and mesh significantly impacts the accuracy and stability of the FSI simulation. For instance, a poorly defined geometry with sharp edges or gaps can lead to meshing errors and inaccurate results. Similarly, a coarse mesh with large elements may not capture the intricate details of the fluid flow and structural deformation, compromising the accuracy of the solution. To ensure accurate FSI simulations, it's crucial to create or import a clean and well-defined geometry. This involves removing any unnecessary details, closing gaps, and smoothing out sharp edges. A high-quality mesh should then be generated, ensuring that it's fine enough to capture the relevant physical phenomena while remaining computationally manageable. Section 6. Achieving convergence and interpreting results. Convergence is the holy grail of FSI simulations, indicating that the solution has stabilized and accurately represents the physical behavior. However, achieving convergence can be a delicate dance, often requiring adjustments to the simulation setup and parameters. Several factors can influence convergence, including mesh quality, time step size, and convergence criteria. A well-defined mesh, an appropriate time step size, and tight convergence criteria are crucial for achieving reliable results. Interpreting the results of an FSI simulation requires careful consideration of various parameters such as pressure distribution, velocity profiles, structural deformation, and stress concentration. These parameters provide insights into the complex interplay between the fluid and structure, enabling engineers to make informed design decisions. Section 7, Benefits of ANSYS Workbench for FSI simulations. ANSYS Workbench offers a plethora of benefits for FSI simulations, making it a popular choice among engineers and researchers worldwide. Its intuitive interface, comprehensive toolset, and robust solvers empower users to tackle complex FSI challenges with confidence. One of the key advantages of ANSYS Workbench is its ability to seamlessly integrate different physics, allowing for the simulation of multiphysics phenomena such as FSI. Its intuitive drag-and-drop interface simplifies the workflow, making it easy to set up and manage complex simulations. Moreover, ANSYS Workbench offers a wide range of material models, boundary conditions, and solution methods, providing users with the flexibility to tailor the simulation to their specific needs. Its comprehensive post-processing capabilities enable engineers to visualize and analyze the results in detail, gaining valuable insights into the FSI behavior. Section 8. Exploring alternative CFD consulting and training resources. While ANSYS Workbench is a powerful tool for FSI simulations, it's not the only player in the game. Several other companies and organizations offer CFD consulting services and training programs, providing alternative perspectives and expertise. These companies often specialize in specific industries or applications, offering tailored solutions and in-depth knowledge. They can assist with various aspects of FSI simulations, from problem definition and model development to result interpretation and design optimization. Seeking external expertise can be particularly beneficial for complex FSI projects or when specialized knowledge is required. It allows companies to leverage the experience of seasoned professionals, accelerating the design process and mitigating potential risks. Section 9. Choosing the right FSI workflow, a balancing act. Selecting the most appropriate FSI workflow is crucial for achieving accurate and efficient results. The choice depends on several factors, including the complexity of the problem, the level of accuracy required, and the available computational resources. For instance, a one-way FSI approach might suffice for problems where the structural deformation has a negligible impact on the fluid flow. However, a fully coupled FSI simulation might be necessary for problems with strong fluid-structure interaction where high accuracy is paramount. The available computational resources also play a crucial role in workflow selection. Fully coupled FSI simulations, while highly accurate, are computationally demanding and require significant processing power and memory. In contrast, simpler approaches such as one-way or two-way explicit FSI are less demanding and can be run on less powerful machines. Section 10. Conclusion. Embracing the power of FSI in engineering design. In the realm of engineering, understanding the intricate dance between fluids and structures is paramount. FSI analysis, with its ability to simulate and predict this complex interplay, has become an indispensable tool for engineers across various disciplines. From designing aerodynamically efficient aircraft and spacecraft to developing reliable biomedical devices and optimizing energy systems, FSI simulations have revolutionized the design process. By embracing the power of FSI, engineers can create more innovative, efficient, and reliable products that push the boundaries of what's possible. As we venture further into the future, the importance of FSI will only continue to grow. With advancements in computational power and simulation software, we can expect even more sophisticated FSI models, capable of tackling increasingly complex engineering challenges. By harnessing the power of FSI, we can unlock a world of possibilities, paving the way for a future where engineering marvels are limited only by our imagination. Section 11. References. 1. ANSYS Inc. 2023. ANSYS Fluent User's Guide. 2. ANSYS Inc. 2023. ANSYS Mechanical User's Guide. 3. Add any other references used in the essay.